just using a problem, we should check if there is a path from source to destination in a given graph. So for that, we saw how first DFS is working, and we wrote a nice recursive code for DFS. After that, I showed you how to write a breadth first search code. For writing a breadth first search code, I did live coding in the session, which was basically just using a queue and putting everything in the queue and removing it from the queue one by one. So there are a few things that I want to address in the BFS code that I have shown you. So we will start from there and then we'll take it forward. Let me just copy all this to our today's discussion. But for writing a breadth first search code, I did live coding. All right, now pay attention, everyone. Now we are discussing. Now we are discussing about BFS. So just to help you jog your memory on how to write a BFS code. So what we basically did is we first created a queue, and then we added the source to the queue, and then we also had a visited array being passed in the parameters, which is basically all false. And you can mark visited of s is equal to true. Or let's say I'll mark visited when I remove it from the queue instead of when I add it to the queue. So I will not write visited over here. So I can directly jump into while not queue dot is empty. Get the current node from the queue. Queue dot pop or remove, whatever it is. Once you get the current node from the queue, we will mark it as visited. Visited of current equal to true. And then after that, we need to add all the neighbors of current, right? So we will loop on all the neighbors of current for each neighbor n for the graph of current. We can add it to the queue. Am I back? Yeah, I'm back. All right, just give me a second to set this thing up. All right, let's continue. I hope you listened to what I was writing till here. Yeah. Okay. Okay, great. Awesome. So the point is, this is not just a general BFS code. Here I did not write, if source equal to destination, then return true, return false, all that I didn't write. You could probably write, somewhere over here. You can check if, current equal to destination, then return true, otherwise return false after the loop. You can write all these things. But here I want to show you one very distinctive thing that we are doing, which is slightly different from what we discussed in our previous session. It is about where we are marking it as visited. So here I'm marking nodes as visited when I'm removing it from the queue. Whereas in our previous discussion, when I showed you the code for BFS, we were marking it as visited when we were adding it to the queue. So the question is, does it matter? Does it matter when you are marking it as visited? Because you're still checking if it is visited or not before you add it to the queue. Does it matter? I mean, should it matter? Will it matter? Can it matter? So let's answer that question. Um, so let's talk about the same graph here that we had above here. Okay, let's start again from traversing from 3 itself. So first, what will I do? I'll start my traversal from 3. I have to maintain somewhere visited or not, right? I'll create probably an array or something like this. And let's say 3 is visited. I mean, 3 is not visited yet. Now you remove it and you mark it as visited. Then you add neighbors of 3 into the array or cube, basically, which are 19, 9, and 2. Then you'll remove 19. You'll mark it as visited. Then you'll add neighbors of 19 to the queue, which are 11. 3 is already marked as visited, 20. Then you'll remove 9, mark it as visited. Then you'll visit all the neighbors of 9, which is just 3. 3 is already visited. Then you'll remove 2 from the queue. Then you'll visit all the neighbors of 2, which are 3 and 10. 3 is already visited. 10 will be added to the queue. And 2 should be marked as visited. Then we have 11. 11. I don't think I'm reaching a point properly here. But yeah, let's just go forward a bit. 11 will be marked as listed. 19 is already marked as listed. It will not be added to the queue. Then go to 20. No more neighbors. 20 is listed. Then we have 10. 10 has 1, 18, and 20. Okay, 1 is already listed. Okay, 1 is not listed. Sorry, 10 should be marked as listed. Then we have 1, 18, and 20. 20 is already listed. And then we have 1's neighbors. Finally, we are here. We remove 1. Then we add neighbors of 1 to the queue. 10 is already visited, so 10 won't be added. 18 is not marked as visited, so 18 will be added to the queue again. 1, 18, 2. That's right. No, 2 is already marked as visited, right? So 2 won't be there. So finally, successfully, I reached the point which I want to highlight to you, which is there are 2 18s in our queue. See, I did not remove the first 18 from the queue. And before I removed the first 18, I got the second 18 into the queue. Because I did not remove the first 18 from the queue, I did not mark it as visited, which is the reason the second 18 was able to enter the queue. So this is, I mean, the example that I have shown you here, it happened only for one element. So it's not an example tailored for showing you how, how tricky this is going to get. But as you can see, if you have a graph that has enough edges, the number of nodes that are going to be duplicated into the queue can be, up to linear time. So each node can be added up to v minus 1 times roughly. And you will end up with a v squared solution instead of a v plus e solution. All these duplicates that are flooding your queue are coming into the queue because of the place you have decided to mark it as visited. This is the difference that is being caused because we have decided to mark it as visited when we are removing it from the queue, which is bad. This will introduce duplicates into the queue, which will cause your code to perform worse and can have a complexity of up to big of v square in worst case for a for a relevant graph. So just make a small note about it that always mark nodes as visited before adding to the queue and not when removing it from the queue. And the reason for that is this method will introduce duplicates into the queue. Mm. 10 seconds, all right. All right, great. Moving ahead then to our next question. So now that we are in a state where we are able to imagine what a graph, how do we traverse it, and how what an adjacency list is, and how do we use it, all the problems going forward, we'll visualize the graph for what it is instead of looking at the adjacency list like we did in the previous problems. So let's start with a simple graph first. Let's say I have a graph like this. This. So the question here is pretty straightforward. The question here is, given an undirected graph, you need to count the number of connected components. Count the number of connected components. Answer for this example is that's right. 4. That is right. Answer for this example is 4. This is 1, this is 2, this is 3. Perfect. That's right. And 4 is the answer. There are 4 connected components in this graph. Take a minute, don't share the solutions in the chat until I ask you to share. Understand the question properly. solutions. Ideas, solutions, time and space, anything. V into V plus C is not exactly the right complexity, though I understand your idea, but the complexity is incorrect there. V plus E comma V, okay, that makes sense. V square plus E. No, that's not the right complexity there. Yeah. So tell me, guys, what do we do? What is the solution here? What should we do? What is the solution here? Counting the breaks between nodes. How exactly do you plan on counting them? For each element, if not visited, call BFS and count plus plus. Yeah, that's right. So the approach here is pretty simple and straightforward, guys. And I would appreciate if everyone was a bit more actively responding. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All right, let's say this is our visited array over here. Let's say this is our visited array here. So the idea is basically you just start from 1. 1 is not visited yet. So we start from 1 and we'll just do a BFS or DFS, doesn't matter, from 1. So when you start a BFS or DFS from 1, you'll visit 1, 2, and 11, and your visited array will be updated accordingly. So you're marking these nodes as visited now. Now all you have to do is go to the next node in your visited array, 2. 2 is already visited, so you don't have to count it. It's a part of some other component that you have already counted. Now go to the next node, which is 3. 3 is not visited here. And the only reason why it won't be visited is if it is in a different component, right, than the one that we visited earlier. So we see that, okay, 3 is not visited. It must be in a different component. Now let's count everything in that component. I mean, let's mark everything in that component as visited, which is nothing but 12, 3, and 4. Now, when you go to the next node, you'll see that 4 is already marked. It's not a new component. 5 not marked means it's a new component. And you will simply repeat what we did earlier. In fact, our logic will basically look exactly like this. For basically, you just have to create a visited array bool, visited of size v plus 1, initialized to false. Initialized to false. Then for I equals to 0 to I less than v plus 1. Not 0 exactly. There's no 0, right? We should start from 1. I equals to 1 to I less than v plus 1. If it is not visited, it means that it's a new component. So we will count it. You will initialize some count equal to 0 or something. And you will simply call BFS or DFS with graph I and visited array. So this is very helpful because we already wrote our BFS and DFS to accept an input, accept the parameter for visited array. So now when you're reusing the visited array, you're just going to mark in the same visited array again and again and again. And it is going to help us count exactly what we need. And at the end, we will return count. So the only change that you have to do in the code that we have written earlier is there is no destination. So you just have to not check for destination in your BFS or DFS. Then it will work normally. Maybe you can write return count over here. Now, if you see here, this looks like it's, V into V plus E. This is V iterations here for the loop. We know that BFS or DFS will have a V plus E time complexity. So it is basically looking like a V into V plus E. That's right, Samuel. But it is not V into V plus E, right? Because here you will visit in your every time you call BFS or DFS, you will never visit any vertex more than once. And you will not visit any edge more than once. So all your BFS or DFS combined will only be big of V plus E. Because they only touch every vertex exactly once, every edge exactly once. Now, if you just factor in the loop here, now it will become something like V plus E. Because this V plus E is combined all the iterations. It is not V into V plus E. It is V plus E. So this is going to come out to be a time complexity of big of V plus E and the space complexity of big of V. And a combination of looping on visited array and BFS or DFS. This is known as a graph traversal. See, if you use only BFS or only DFS, there is absolutely no way that you can touch all the nodes of the graph, right? It will be limited to whatever component you have started in. Repeating my point again. If you're using only breadth first search or only depth first search, you cannot go to any node beyond the component that you have started on. So breadth first search and depth first search by themselves are not exactly traversals. They don't touch your entire graph. Breadth first search, depth first search combined with looping on the visited array like we have here will count as a graph traversal because this code that we have written will touch every single vertex of your graph. So if you were using a breadth first search here, it would have been a breadth first traversal. And if you were using a depth first search here, it would have been a depth first traversal. So depending on what you are using, BFT or DFT. And if I go back here to the BFS code that we have written, just a side note here that if you want to write iterative depth first search, all you have to do is replace Q with a, if you want to write an iterative depth first search, that is right. Simply replace Q with a stack and don't change absolutely anything in your code. Just replace Q with a stack. Then it will become an iterative depth first search. Just add it as a side note in your BFS DFS discussion. Let's say you are given these three graphs, graph 1, graph 2, and graph 3. Can you tell me which of these graphs is a tree? Which of these graphs is a tree? There might be more than one answers. Okay, okay. 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 So first, let's try to understand. Why do you think one is not a tree? Why do you think graph number one is not a tree? Loop is different, cycle is different. Loop is a self-edge, cycle is this. That is right. So we understand that for a graph to be a tree, one of the properties that it should have is it should be acyclic. There should be no cycle there. Since graph number one has a cycle, graph number one doesn't exactly count as a tree. Can you tell me why do you think that graph number three is not a tree? No link break between nodes. Seriously, are those graph terms that you're using there? Thank you. The graph is disconnected. That is right. The graph is disconnected. So you're saying that because the graph number three is disconnected, it is not a tree. Means you're saying that for a graph to be a tree, it should be a connected graph. That is right. The graph number three has two connected components or two components in short. But connected graph is just one component. So you are saying that because of these two reasons, graph number two is a tree, and that is correct. In this examples, only graph number two is a tree. For a graph to be a tree, it has to be acyclic and it has to be connected. But you already know how to check if a graph is connected, right? Don't worry, I'll give you time to write down. You already know how to check if a graph is connected, right? Yes. How? And that's it. Perfect, guys. You just have to check if the number of connected components. Exactly. You just have to check if the number of connected components is exactly one, which is basically our previous problem. So we already know how to check if a given graph is connected or not. So the only thing that you have to focus on in this problem is to perform cycle detection. So focus on that part of the problem, not on the question, write on the examples properly, clearly, and focus on how to detect a cycle in a graph. Also, some of you do not have your videos on for a long duration. Please turn it on or I'll have to remove you from the session. Some of you have the video on, but it is a blank screen. Shrija and Sudhir. Please make sure you have your face visible as well. focus on how to find if there is a cycle in the graph. And when you're doing that, don't think that it is obvious. Oh, if I come back to that node, it's a cycle. There are other ways to come back to that node, even without a cycle. Any ideas that you have, you can share. Everyone is just waiting for others. Using DFS, if visited node is updated again, then there's a cycle. If CAvert is again as visited while performing DFS, we can say there is a cycle is present. If there are more than one path for a node, okay. Any other answers? BFS of source, source, then cycle. It will return true from the beginning itself. Create a direct graph, the same graph, and can do visited based on it. Okay. If it was using DFS and if any neighbor of a node is visited and we did not reach that neighbor from the visited node for which we are checking neighbors, then cycle. Okay, that makes sense. That's a good direction there. BFS for loop when you have logic in place. If visited are equal to false, else in cycle found. Not exactly. For each visited node by unvisited edge. Yeah, that makes sense. So first we'll try to understand. Okay, let's discuss the solutions and we'll try to understand why the obvious solution doesn't work, which is if I come back to that node, there is a cycle. I mean, it feels obvious, and that's probably where we should start from, right? So the problem is, let's say I mean, it doesn't matter where you start your traversal from. Let's say I start from 8. I'm just doing this logic of if I come back to that node, there is a cycle. So I go to 8. I mean, I start from 8. Now I check the neighbors of 8. Neighbors of 8, only 7 is there. Only 7 is there. So from 8, I'll go to 7. Okay, now 8 is marked as visited already. Now I am at 7. When I'm at 7, now I want to visit all the neighbors of 7. To visit all the neighbors of 7, what will I do? I'll visit 6, I'll visit 9, I'll visit 10, and I'll visit 8. Done. Cycle. So the problem is you don't know if you did this to come back to 8, or if you're just going back and coming down the same route. You're coming back to 8 again. So you cannot differentiate it just like that. So the solution is not as simple as if I come back to that node, there is a cycle, because you will come back to that node definitely from the node that you went to, because you're a neighbor of it. So that strategy has to be refined a bit. You need to, say it in a better way. If I come back to this node in some other way, then there is a cycle. Okay, now let's say now I am doing a simple BFS or something like that. I start from 8, I'll visit 8, then neighbors of 8, which is 7, the neighbors of 7, which are 6, 9, and 10, the neighbors of 6, which are 5 and which are 1. Then I'll visit neighbors of 10, the neighbors of 9, the neighbors of 1. Neighbors of 1 are 5, 11, and 4 and 2. Then I'll visit neighbors of 5, then I'll visit neighbors of 11, then I'll visit neighbors of... Okay, yeah, now I'm visiting neighbors of 11 here. So the way, when I'm at 11, now I know that this is going to be a cycle. But how will I know that it is going to be a cycle? When I'm at 11, you can see that there are 2 visited neighbors before I started visiting the neighbors of 11. Both 1 and 4 are visited. And it is possible only if there is some other path to reach 1 and some other path to reach 4, right? And out of 1 and 4, one of these nodes has to be the node from which you came to 11. So you'll expect, one of the nodes to be true. One of the neighbors to be true. But expecting another neighbor to be true, that is not what we want, right? That is not what we expected, basically. It means that there is some other way to reach 4, other than coming from 11. Which says that, hey, there is a cycle here. So let's do it for a different node. Instead of visiting the neighbors of 1 in that order, let's say now I'll visit neighbors of 2. When I visit neighbors of 2, before I started visiting them, how many neighbors are marked as true? 1, exactly. So there is exactly 1 node which is marked as true. And that is nothing but the node which inserted 2 into the queue. So, okay, now let's say I will visit all the neighbors of 2. Then I'll go to 3, for example. Now, when I go to 3, before I started visiting the neighbors of 3, you can see that there are 2 nodes which are already marked as visited. 1 node is probably going to be the node from which 3 was added to the queue. That will be marked as true anyway. But the other node, that should not have been marked as true. And that will be marked as true. Here in this case, 4 is marked as true. Only possible when there is another path to reach 4 other than 3. So you could reach 4 in some other path other than coming from 3. Means there's a path to reach 4 from here, and there's a path to reach 4 from here, indicating that there is a cycle there. 2 is expected, 4 was not. So there's a path to reach 4, which doesn't include 3. So there is a loop. That is right. Exactly. So this is one way of detecting a cycle, which is the number of unvisited neighbors. If the number of unvisited neighbors is greater than 1, then there is a cycle. You need to check this before you start visiting them. After you start visiting the neighbors, obviously you'll mark them as true. So this should be checked before you start looping on the neighbors. Number of unvisited neighbors greater than 1, then there is a cycle. Yeah, it's not unvisited neighbors, guys. My bad. It is number of visited neighbors. Number of visited neighbors greater than 1, then there's a cycle. Thank you, Prem. Seven to six, 6 to 1, and 1 to 6 will be having 2 visited neighbors. But you're visiting already the neighbors of 6 there, right? So you're checking after visiting the neighbors of 6, which is incorrect. You should check before visiting neighbors of 6. So the first time you come to 6, only 1 visited neighbor was there. Now let's see what other way is there to check. So we are checking visited neighbors greater than 1 because we know that there will be at least one node. That node would have been the node which was responsible for adding the previous node to the queue. For example, when you are at 2, you are adding 3 to the queue. So if A is adding B to the queue, then we will call A is parent of B. Then we'll simply call that A is a parent of B. Parent in this case is not very defined like it was in trees. Here we are just defining a parent based on our requirement. That's it. Whichever node adds the other one to the queue, that is a parent. So we are basically checking if other than parent, is there any other node which is already visited? Our entire check is based on that. So you can say that that is another way of checking visited neighbor other than parent. We have a visited neighbor other than parent. Now you can say that, okay, can we do something with edges? So if along with marking nodes as visited, if we could mark edge also as visited, then can we do something? Let's say I'll start at 9, then I'll go to 7. I'm doing a depth first search type of thing here now. Then from 7, let's say I'm going to 6. Let's say from 6, I'm going to 1. Let's say from 1, I'm going to 5. Then I'm going to 2. And let's say I'm going to 3. Let's say then I'm going to 4. And let's say then I'm going to 11, and then I'm going to 1. So the idea here is Doesn't matter if it is a depth first search or breadth first search. If you observe from 11, I can reach 1. Means from the current node, I'm able to reach a visited neighbor. I'm able to reach a neighbor which is already visited via an unvisited edge. So if you're able to reach a visited neighbor via unvisited edge, again, it means that there should be some other path to it other than this edge, indicating that there is a cycle, which is nothing but our approach number 3. If we can reach a visited neighbor from an unvisited edge, then comes the 4th ultimate way to check if there is a cycle. Before we move to the 4th way, let's talk about first this point. How do you mark edge as visited? What will you use to track which edge has been visited? Perfect. Exactly. Matrix. You need an adjacency matrix. Recollecting to the previous discussion, there is only one benefit with adjacency matrix, right? Which is direct access, direct edge access. Exactly. You get direct access to the edge. And that one benefit is the only thing which can help you do this. Tracking which edges have been visited already. All right, now let's come to this point 4 of cycle detection. Now imagine that I start with one node. Okay, this is a completely different graph, not related to the previous one. Imagine that I start with one node. And every time I add a node, or every time I try to add a node to this, it will come along with an edge attached. Means if I want to add 2 to this graph, that 2 will come with the edge attached to it. So I can attach it anywhere. Maybe say I will attach it over here. And let's say we are getting 3 next. 3 will come with an edge attached to it. I mean, just imagine, you'll not exactly get like that, but let's imagine you are getting it like that. Then wherever you put 3, let's say here or here, doesn't matter. Let's say I put here. Then let's say now I'm getting 4 with an edge attached to it. Now, wherever I put 4, here, 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 it doesn't cause a cycle, right? No matter where I put 4, it doesn't cause a cycle. Similarly, let's say I'm getting 5. Now, wherever I put 5, here, 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 do you see that it doesn't cause a cycle? So the reason why these things are not causing a cycle is because the node is always coming with an edge. If I send you just an edge separately without a node and I ask you to put it somewhere, no matter where you put it, it will definitely cause a cycle here, right? This edge, no matter where I put it, like I put it here, or I put it here, or I put it here, or I put it here, no matter where I put it, it will definitely cause a cycle. So what this points to is basically, as long as the number of vertices is equal to number of edges plus 1, exactly. As long as the number of vertices is equal to the number of edges plus 1, it doesn't cause a cycle. That's right. So let's say I put 6, let's say I put 7, let's say I put 8, 9. But the instant that I introduce only an edge, then it will start to cause a cycle. So we can do this check to check if there are cycles without actually traversing the graph. But there's a small hiccup. If you look at this graph, for example, v equal to e plus 1 is satisfied, right? But it is not following our principles that it doesn't contain a cycle. It has a cycle. So this v equal to e plus 1 will only work if the graph is connected. That's right. If the number of connected components in our graph is exactly 1. Make a quick note of it. These are all the different ways in which we can do cycle detection in an undirected graph. Now, going back to our examples above, the example 1, 2, and 3. Can you say that this graph contains two trees? Can you say that this graph contains two trees? And what do you call a collection of trees? Yep. A forest. Yeah, I admit that two trees don't make up a forest, but in general, a collection of trees is a forest. So this is also a forest. Moving on to the next question. Moving on to the next question. Given an undirected, unweighted, simple, connected graph, or you can just write it as given an undirected graph. And two nodes, the source and destination. Let's say this is source and this is destination. You're asked to calculate the length of the shortest path between these two nodes or from source to destination. Calculate the length of the shortest path from source to destination. For example, if you look here, if I go in this way, 1, 2, 3, 4, 5, 6, 7. But if I go in this way, 1, 2, 3, 4, 5, 6. And if I go in this way, 1, 2, 3, 4, 5. So clearly different paths have different lengths. And for this example, this is the shortest path with length 5. Tighten the question properly, completely carefully. Don't share your solutions until I ask you to share, and jump in. Solutions. Ideas, solutions, anything? At least ideas. Using depth for search until we reach the destination. Okay. Traverse all paths and find mainland using visited array. Okay, that makes sense. Find all possible paths from source to destination. That's right. Depth first search. Construct a minimum spanning tree. Definitely not relevant here. First taking neighbors of source in queue, then checking to destination and calculate the length of the queue. Checking the length of the queue. No, definitely not. Minimum of number of nodes for each path from source to destination. Firstly, you should count the number of edges, not number of nodes. And secondly, that is basically redefining the problem once again. So, okay, first we'll hey, don't say sorry. It's fine to give wrong answers. We are learning here. Just letting you know what is wrong with it. That's it. Yeah. So, firstly, the problem with depth was such. The problem with depth first search is we can't do anything for certain. And you can't really, say that, okay, let's say I start from 10, I'll go to 1. Now you can't tell depth first search if it will go to 2 from here, or if it will go to 3 from here, or it will go to 5 from here. Okay, let's say it went to 1 from here. Sorry, 10, it went to 1. Let's say it went to 3 and then to 2. That's another direction that you want. So the problem with depth first search is you can't really control which is the direction you want to go. You don't know which direction you want to go first. And depth first search will just pick randomly, it will go in that direction. That's it. Not randomly, based on the input order in your adjacency list, basically. But that is not good for us. That will not ensure that you're reaching destination in the shortest path. It will just reach the destination, that is guaranteed. But it will not ensure you're reaching it in the shortest path. So depth first search is helpful when you are doing the other brute force solution, which is check all possible paths to reach destination and then decide which is the shortest one. So what your depth first search can do is when it goes to 1, it will try going via 5 first. Let's say you found destination, then it will backtrack and it will try going via 3. Then it will backtrack and it will try going via 2, and so on. DFS plus a bit of backtracking can help you check all possible paths to destination. And you can pick whichever is the minimum. So that is, we can call this our solution 1. However long that takes. But true power comes, or the next ultimate solution comes in the form of comes in the form of BFS. BFS, guys, is the ultimate solution here, and BFS will show its true colors here. If you recollect back to our trees discussion, I told you something about BFS. I told you that, if you remember, level order is same as BFS. So you can imagine that is exactly what is happening around here. Let's say I will start my BFS from the node 10. Now I will first visit all the neighbors of 10, which are 1 and 9. Then I'll start to visit all the neighbors of 1, which are 4, 5, 2, and 3. So 4, 5, 2, 3. See here, guys, 10 is a node at level 0, distance 0 from 10. 1 and 9 are nodes at distance 1 from 10. And 2, 3, 4, 5 are nodes at distance 2 from 10. Now, whichever are the neighbors of 2, 3, 4, 5. So neighbors of 3, you will get 6. Neighbors of 5, you will get 7. That's it. These are nodes at a distance 3 from 10. Oh yeah, we also have 11 for 2. All these are at a node distance 3 from 10. So I hope you can correlate here, right? How our level order worked. It will go level by level, right? That is how BFS is going, level by level. First level, all nodes at level 0, all nodes at level 1, then all nodes at level 2, and so on. So this is basically checking every node at distance 0, then every node at distance 1, every node at distance 2, and so on until it is exhausting all the nodes. Then obviously, whichever node is the destination, it will be found at the shortest distance from 10. Because you're checking every node at every distance, starting from 10. And that is how BFS will guarantee you shortest path to destination. Because it will check every node at every distance incrementally. So now obviously it is going to be a challenge here, right? To identify a change in level. How do you know at what distance you are from 10? Because you're only using a queue and a visitor array. But we already solved that problem in level order traversal, right? 7 different solutions. Yeah, marker nodes, parent node, queue of pairs, 2 queues, etc., etc., map, vector, size of queue. You can use any of the solutions, whatever will fit here. And you can use it to track change in level. So use solutions from our level order traversal on tree discussion to count length of the path. All the level separation solutions that we discussed will work here. Shall we move on to the next question then? All right, 30 seconds. If they ask to print path, not length, then what do we do? That's a very good question. If they ask you to print the shortest path, the entire path, now you're only concerned with which node added that node to the queue, right? So at the end, if I continue like this, next, I don't have place here. Let's just move it like this. In the next level, 6 will add 12. And in the next level, 12 will add 13. So when you reach 13, you'll know that, okay, I have reached my destination. So all you have to know is which node added 13 into the queue. That was 12. So you need to store this in an array, like a previous array or a parent array. And which node added 12 to the queue? That was 6. Which node added 6 to the queue? That was 3. Which node added 3 to the queue? That was 1. And which node added 1 to the queue? That was 10. So all you have to do is keep track of the parent as we defined it in the previous problem. Parent is nothing but the node which is adding the other node to the queue, right? So if you simply keep track of the parent, all you have to do is from the destination, go parent, 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 parent until you come to source, and that is your path. Moving on to the next question, you're given an undirected, unweighted, acyclic, connected, simple graph. Undirected, unweighted, acyclic, connected, simple graph. Undirected, unweighted, or cyclic connected simple graph is nothing but a, yeah, tree. Exactly. You need to find, you need to find the length of the longest path in the graph. Find the length of the longest path in the graph. And what is the answer for this example? And between which two nodes? Answer for this example, and between which two nodes do you have that path? Ten to 18. Ten to 13. Okay. 18 to 20. You should tell me the length as well, by the way, not just which nodes. Ten to 13. Length 11. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Just 10, right? How did you get 11? Or did I count wrong? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Nodes. No, you will not count nodes. Definitely not, right? You just miscounted, right? You are not counting nodes, right? Tell me you miscounted and you did not count nodes, please. Yeah, thank you. Thank you. Thank you. Because we already discussed a lot of times, including in trees, that you will never count nodes, you will always count edges. So I'm fairly confident on you guys that you are paying attention to me in my class and you remember at least some things, if not everything. 1, 2, 3, 4, 5, 6, 7, 8. Okay, 18 to 20 is just 8. And yeah, I mean, clearly here, 10 to 13 is the longest path. There's no denying that. Let's add a small what do you say, edge. Let's add a small edge here. 15 will have maybe 19. Okay, 19 is already there. 20 is already there. 21. Then it'll be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? Yeah. So we have two paths here now. Both of length 10. So answer is 10. It could be between 10 to 13, or it could be between 21 and 13. That is a question. I'll give you a minute. Write on the question, properly, completely, carefully. Don't share solutions in the chat until I ask you to share. Take a minute and come up with some nice solutions here. Try to use your brain a bit more. This is a very simple problem. At least to get one or two solutions. All right, solutions, ideas, solutions, whatever you have. BFS from every node to last, any node to last node, BFS on every vertex and take max level. Okay. Any other ideas? V into V plus C. Okay. Brute force for all nodes, find all possible paths and find max length. We'll be counting each path twice. Those who can be avoided. Yeah, you can think of it like that. You can think of it like that as well, or you can simply do a BFS from every vertex, which is also relatively the same. Any other solutions? BFS from leaf nodes to leaf nodes. I mean, you will not really know which is a leaf node, right? Or you can say that any node which has only one edge is a leaf node. Yeah, single edge, probably. Yeah, I mean, that makes sense. It will narrow down the number of possibilities a bit, but the worst case will still remain the same. So obviously, the brute force solution here is simply do a BFS from every vertex, because you know that BFS goes level by level. So whichever is the maximum level that it will go to, that is the maximum length of path that you can get from that node. So all you have to do is repeat the BFS for all the nodes. For each node, count what is the maximum BFS level that you're getting and update your answer. So there's a simple brute force solution, which is BFS from every node. From every node. Let's say I pick any node. Let's say, for example, I'm picking the node 17. And let's say I want to do a BFS from there. I'm picking in the node 17 and I'm doing a BFS from 17. So 17 will add the neighbors 18 and 16. 18 will not add any neighbors. 16 will add 8. 8 will add 2 and 6. 2 will add 1, 9, 19. 6 will add 5. 1 will add 14. 9 will add nothing. 5 will add 12 and 7. 14 will add 4 and 11. 4 will add 3. 11 will add 20 and 15. 13 won't add anything. 3 will add 10. 20 will add nothing. 15 will add 21. 10 and 21. Similarly, you do a BFS quickly from another node and tell me what is the last node that you're getting. Do a BFS from any node. Obviously, don't pick the answer nodes. Any other node other than answer nodes. And tell me what is the last node that you are stopping at. Fast, guys. I mean, by now you're good with BFS. So it should be fairly easy for you to do it. Just say done once you're done. Done. If you're done, you can share like which node you started and which node you ended with. Starting node and ending node of your BFS. 821, 12, 20, 21, 13, 21, 12, 21, 5, 21, 12, 21. Did no one start from 11, 4, 3, 15, 12, 21, 6, 21. Okay, 9, 21. Others, anyone started using these nodes? Eleven, 13. Okay, that's promising. Great. Others, what about you? Where did you start and where did you end? Two 21. Okay. Okay. 12, 10. Yeah, it's possible. Okay, 12, 10. 2, 13. Yeah, okay, it's possible. Yes. 2, 13. Yeah, makes sense. So, what do you guys observe from all the answers that you have given? 15, 13. Okay, that's nice. What did you guys observe from all the answers that we received in the chat? Start from any node, last node equal to longest path. One of the ends of the longest path, yes. Depends on which node which we traverse next. Yeah, that is also there. But that is not the main concern for us in this discussion. So if you observe, whatever answers that you guys have shared, all the nodes that you have ended with, they are ending with either 13, 10, or 21. Only one of these nodes, right? All the answers that you guys have shared are ending with either 13, 10, or 21. Which is basically you're always ending with one of the ends of the longest path. If you have one of the ends of the longest path, how will you get the other end? Exactly. Exactly. Perfect. Perfect. BFS from that end, you will get the other end. BFS from 13 will give you 21 or 10. BFS from 10 or 21 will give you 13. So the solution is basically do first BFS to get one of the ends of the longest path. And from there, do the second BFS to get the other end of the longest path. And as we saw clearly, it doesn't matter where you start the first BFS from. You can start your first BFS from any node. And you will always end up with one of the ends of the longest path. And to get the other end, do BFS from there. All right. Last 10 seconds. Now, this graph, we said that, okay, it is an undirected, unweighted, acyclic graph. What if the graph is cyclic? What if the graph is a cyclic graph? Time complexity, you know the time complexity of BFS, right? Time and space. So it is just 2 into that. Yeah. Now, what will happen, guys, if there is a cycle? Why is this solution only for acyclic graph? Why not any graph? Longest path in a cyclic graph. Infinite length. See, whenever you calculate a path, you will never visit the same edge again, right? So this is not a problem of infinite length here. You will not visit the same edge again. So it's not like, you will go like this. That will not happen when you're calculating a path. You will maybe go like this. So the problem with finding the longest path in a cyclic graph is that it is an NP hard problem. Or is it NP complete? Most likely it is NP hard. You can check up on Google if it is NP complete. But it is definitely NP hard problem. And this is a good starting point for you to understand P versus NP. I gave you a to-do sometime back, I guess, right? To learn about P versus NP. Polynomial problems which can be solved in polynomial time and problems which can be solved in not deterministic polynomial time. NP is basically a non-deterministic polynomial. So in non-deterministic polynomial time, when you say P versus NP, you often say that P is polynomial, NP is non-polynomial, which is wrong. Don't say it is non-polynomial. It is non-deterministic polynomial time. And write this as a to do. It's a very nice to do. And if you are interested in Max, especially, this is a very good place to start with. And if you say no, I don't like Max, still you read about it, because ultimately computer science is just automated Max, right? Um, Moving ahead to our next question, then, which is one of the good, interesting questions in graphs. And very popular question as well. Yeah, I think this is good enough. So in this question, basically, 0 is water, 1 is land. You just have to count the number of. That's right. Count the number of islands. You can assume anything beyond the boundaries is also water. Anything beyond the boundaries of the matrix, you can assume it is water. For this example, can you tell me what is the answer? What is the answer for this example? 6, 4 others. 4, 4, 4. Four. So the answer for this example is yeah, 2 sounds more like it. That's the right question, Parthiban. So first you need to understand from one land, in what directions can you move to the other land? So this is what we call a neighborhood. Which directions do you consider as neighbors of the current node? If you consider that, okay, I can move in only 4 directions, then this will become something like this. This is one island. This is the other island. This is the other island. Oh, sorry. And this is the other island. So if we are considering N4 neighborhood, we can say that the answer is 4. But if we have to consider An 8 neighborhood means you can go from one cell to the next, even diagonally. Means diagonal cells are considered neighbors as well. If you consider an 8 neighborhood, then you can see that from this one to this one you can travel. From this one to this one you can travel, making this entire thing as one island. And this thing is the other island. If it was an innate neighborhood, the answer would be 2. Depending on how the neighborhood for moving around is defined, or how the neighborhood is defined. N4 neighborhood or N8 neighborhood. For this example, we will consider N4 neighborhood. For our discussion, we will consider N4 neighborhood. And we will proceed with the discussion of the solution. I have enabled mark activity, everyone. Please mark your activity. Mark activity has been enabled. Please mark your activity, guys. And we will meet again at 6:21. And meanwhile, try to think of few approaches about this question as well. What exactly do we do here? How is it related to graphs? How do we count islands? How do we know which is an island? Etc. etc. Mark your activity and we'll meet again after the short break.
Recording stopped.
ఎందుకు Jayant, please join the breakout room. Jayant, please join the breakout room. All right, everyone, let's begin. Let us begin, everyone.
Recording in progress.
Videos on, face visible. We will start with our discussion. Faster, guys. Videos on, face visible. We'll start with our discussion. Faster, please. Let me just stop and reshare my screen once. I'll just reshare my screen. Right, I think that's better. Solutions, guys. Solutions for this problem. What do we do? Solutions for this problem. What do we do? Share your ideas. Can we somehow transform it to a graph and do connected components? Okay. Others? Approach, what do we do here? Start with one, mark all connecting vertices, repeat until all ones are marked. Okay. Others, solutions, ideas. For n equal to 4, we make a graph from the matrix and count the number of disconnected graphs. You mean number of components? Yeah, you could do something like that, probably. First step, consider this as an adjacency matrix. Okay. Not necessarily. If you consider it as an adjacency matrix, the meaning will completely change. All right, let us discuss the solutions, everyone. Constructing graph with matrix link between vertices with 1 as value in matrix. Number of connected graphs will be the number of islands. Can you do something with recursion? Okay. All right. So, guys, let me help you with that first. Firstly, converting this matrix to a graph, basically. That's a completely viable solution. But we don't have to do that. You can consider it as a graph here itself. See, the entire point behind why you want to convert it to a graph is basically because you know how to traverse on a graph. So you want to relate it to the connected components problem and say that, oh, this is connected components. I will do it like that. But you can do it directly here. See, you know that for any cell, all 4 directions are the neighbors. So you already know that if you see a 1, that all the 4 directions connected to that one will be the neighbors of this one. Means you already have enough information here to consider it as a graph. So all you have to do is, first you come here. Just traverse on the matrix. Here, here, here. And here you see a 1, right? So what you do is, once you see a 1, you traverse that entire island and mark everything as visited. Traverse that entire island and mark it as visited. So once you mark it as visited, now when you go to the next one, it is already marked as visited. So you'll not count it, you'll simply ignore it and you'll go to the next cell in the matrix, the next cell in the matrix. Now this is not visited, so you have to mark this as visited. So you'll traverse this entire island and mark it as visited. And so on. For you to mark these cells as visited, what do you need? For us to mark them as visited, what do we need here? Yeah, BFS or DFS, but where do you store that information that it is visited? That's right. You will maintain a visited matrix, right? You will maintain a visited matrix. Initially, visited matrix will contain all false. Now, whenever you're visiting, let's say the first line, first you'll mark it as true, 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 like this. Visited matrix is also, visited matrix is basically a Boolean. And 0, 1 matrix is also basically a Boolean, right? Exactly. That's right. So this information, instead of maintaining it in a separate visited matrix, you can maintain it in this itself. By simply saying that if I visit a node, I'll simply convert it to 0. Because 0 anyway we ignore. Following? Kind of. Maybe. Yes. Okay. Yes. Repeating once again. Instead of marking nodes as visited in a visited matrix separately, I am suggesting you that you simply convert 1 to 0 to indicate that they have been visited. Because zeros are anyway ignored in our logic. Now everything simply boils down to the implementation of BFS or DFS that we're doing here. So we understand that we visit every cell. We understand that whenever you see a 1, you'll visit that entire island, marking it as visited. And we do that until we visit all the islands. Of course, in that process, you'll count as well. So everything now boils down to how do you write a BFS or DFS, which will run on a matrix. Let's start with a depth first search. To simplify my approach, to simplify the code that I'm going to write, instead of handling the base condition in 1, 2, 3, 4 directions, I have to handle the base condition when I'm trying to go up from this cell, right? And to go right from these cells, and to go down from these cells, and to go left from these cells. So there are 4 different base conditions that I have to handle. So instead of writing base conditions like that, what I'll do is, tell me what should we do to simplify it? We discussed a similar idea earlier, if you remember. Zero row and 0 column. That's right. 0 additional column, 0 additional row, but not on one side, right? On both the sides. You add a row on both the sides, you add a column on both the sides. If the previous matrix size was n cross m, what is the new matrix size? What is the new matrix size? Perfect, exactly. N plus 2 cross n plus 2. N plus 2 cross n plus 2. Perfect, exactly. We added two rows, one at the top, one at the bottom, and we added two columns, one at the left and one at the right. N plus 2 cross n plus 2 is the size of the new matrix. So if you remember, we did this back in knapsack problem by adding an additional row. We also did it in that matrix count, how many parts are there, that problem, by adding an additional row and additional column on top and left in dynamic programming. And now we are doing it again here in a graph problem because it will just simplify our base conditions. Considering all of this, now all I have to do here is write a DFS code, or maybe I'll write at the bottom. We just have to write a DFS code. Void DFS, you are basically getting a matrix in the input. What other parameters do we need? What other parameters do we need? You don't need the number of rows and number of columns. That is why we added this additional row of zeros and ones. Yeah, but you need the index at which you are present. That is right. You need the index at which you are performing your DFS from. You need ing. Exactly. I think that is all we need, right? Visited matrix is not required because we are simply making them 0. So keeping all this in mind, can you tell me what should be the base condition here? What should we write as a base condition here? Equals to 0. Mat of ij equals to 0. Perfect. If mat of ij equal to 0, return. Perfect. Exactly. That is our base condition here. That is why we also added that additional row and column of zeros as well to simplify our base condition. If you did not add that additional row of zeros, row and column of zeros, then you will have to write if I greater than or equal to 0, if j greater than or equal to 0, if I less than n, if j less than m. And you have to pass n and m also in the parameters. Instead of that, writing like this is much simpler. Okay, now this is done. Now we need to mark it as visited. So we already know how to do that, right? We simply say, exactly, mat of ij is equal to 0. 0, perfect. If it is 0, you return. If it is not 0, you make it 0. And now you just have to repeat this process for the 4 sides. I think you can see what is coming in front of us here. DFS, 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 right? N4 neighborhood, 4 sides. Go up. Go right. Go down. And then go left. And then go left. make a note of it till here. Then I'll explain you a few more points around this. Last 30 seconds. Just a second, guys. Yeah, let's continue. So here, here, if you have to do a BFS, for example, now what should you add in your queue? What should you add to the queue? Yeah, neighbors, but what information about the neighbor are you adding to the queue? Index, pair, I comma j. Exactly, perfect. You need to add the pair. So your queue should be of type pair here. So when you remove any I comma j index, you need to add I plus 1j, then you need to add ij plus 1, then you need to add, and so on. You get it, right? Then ij minus 1, maybe I minus 1j, maybe something like that. You need to add pairs. You need to add both row and column of the next cell that you are going to visit. Obviously, you'll not add those cells which are already marked as visited or basically which are 0. And using this, I'm sure you can write the rest of the BFS code very easily. So just make a small note of this, that if you have to write a BFS, then you need to write it with a BFS containing a queue of type pair. Now let's say that instead of N4 neighborhood, now I am upgrading it to an 8 neighborhood. Then what will change in our DFS code? What will change in our DFS code if I upgrade it to an 8 neighborhood? 4 more DFS, 8 DFS calls. Exactly. Then we will have DFS for diagonals as well. That is right. So instead of 4 DFS calls, now you'll write 8 DFS calls. See, writing 4 DFS calls was itself, slightly not very comfortable for us. And writing 8 DFS calls, and if you make one mistake with I or J anywhere, it will be a pain to debug what is going wrong. Not only that, now you are just, doing repetitive logic. Instead of that, you could have done with something like a loop. So if you can simplify it, instead of writing 8 function calls, if we can write a loop which will call it 8 times, then it will be much more simpler and much more controlled for us. See, if I go back to this any neighborhood and zoom in on this. Okay. So here, basically, this is, let's say this is I comma j. And let's say this is I comma j. So the directions for I and the directions for j that you have to visit are simply, first you'll visit, let's say top left. Top left is -1, -1. So you'll do I -1 and j -1. Then you'll go up, which is basically -1 and 0. Then you'll go here, let's say this is -1 and 1. Then left is basically 0 and -1. And right is 0 and 1. And bottom left is something like 1 and -1. Then this is 1 and 0, and this is 1 and 1. 1, 0, and 1, 1. So do you understand what we wrote here? So if you have -1 and -1, it's basically meaning that we are going from ij to I -1, j -1. For example, if you have 0, 1 here, means we are going from ij to ij plus 1. 1, 1 means we are going from ij to I plus 1, j plus 1. So we basically created an array here. Index 0, index 1, index 2, index 3, 4, 5, 6, 7. Right, which we can loop to add the direction of I to it and the direction of j to it. Getting the idea? You don't really have to write a loop to generate this. Just generate it or write it, hard code it, and then loop on it to loop on all the neighbors. It's just 8 indices, so you can hard code it. Are you following, guys? Are you with me? Good. Got it? Yes. Okay. Yes. Great. So if I try to apply this in our DFS code, then our code will look something like this. YDFS, int mat, everything will remain the same. And I and j. You will declare your both the arrays here. And we can write base conditions mat ij equal to 0, or you can declare them globally, anything is fine. Mat ij is equal to 0. And then you'll run a loop. K equal to 0 to k less than or equal to 7 or k less than 8. And then you'll simply call DFS with these two things, right? I plus di of k, j plus dj of k. Di and dj are arrays you have to declare somewhere in the function or declare it globally. Doesn't matter where you're declaring it, but this is how you are going to use it. So di and dj will help us with the directions for I and j, in which we need to call the neighbors. Please make a proper detailed note of it. This is a very common discussion in interviews, which ask you to write codes for matrix-based problems. Last 30 seconds. Where are we counting? So the part where we are counting is not included in our discussion because we already know how to do traversal matrix and how to call DFS and BFS. So that part did not come in our discussion. The part where you do it will not be inside these functions. You have to write a separate place where you're calling these. There you will count. Similar to our connected components problem. Before we move on to the next problem, there's a very important message that I have shared on Discord, I think last week, for which I still did not receive much response. I want you to revisit that message once again and follow all the instructions that are given there. And let's dedicate 5 minutes for this exercise. And I am tagging you guys so that you know what message I am talking about. And once you're done with following the steps, then you can simply select the tick mark and let me know that you have joined the group successfully. Obviously, joining the group will involve you to use the bot commands. I hope you remember how to use bot commands. You used them when you were joining the group for B29 as well, right? We'll dedicate exactly 5 minutes for this exercise. Everyone, please do it right now. Once you have joined, just select the check mark icon so that I know that you have joined. If you did not join right now and use the bot commands option there to just do the login steps. /login username, then /OTP, give the OTP. Automatically join. It will not join automatically. You need to do the /login commands and everything. So by joining, if you mean that you have joined the server, that's different, and using the bot commands is different. I hope you know the difference. If you just join the server, you'll be able to see only like 2 or 3 channels. But to see all the channels, you need to use the login commands to verify that you are a student of Smart Interviews, so that you can see all the other channels that are there. /login, give your Smart Interviews username, then you'll get the OTP, then use /OTP to give the OTP. Let's dedicate 4 more minutes for this exercise, guys. Let's do it right now. You need to give /OTP space OTP. Done. Yeah, you're done. Faster, guys. I see many of you have joined, but you did not use the bot commands yet. You should use the bot commands. Go to bot commands channel, enter /login space Smart Interviews username. Done. You need to use the forward slash to indicate that you're entering a command there, so that the bot can understand it's a command and it will try to interpret. Done. Done. Come on, guys. Last 3 minutes for this exercise. Let's do it fast. Go to bot commands, use the /login and /OTP commands. /login and /OTP. Done. So you need to give your Smart Interviews username, the same username you use to log into Smart Interviews website every week. Come on, guys, 2 more minutes. Let's do it. Guys, you should give the username, not name. I hope you know the difference between username and name. Username is what you use to log in to Smart Interviews website every week. Faster, guys. I still see many of you did not use flash login, the login commands. Let's dedicate 1 more minute for this. Please do it right away. Done. Faster, guys. Last 30 seconds. All right, moving ahead. So that alumni channel will be on that. You will be getting a lot of what do you say updates from us. You'll be getting interview opportunities. You'll be getting yeah, people will be sharing their interview experiences. You can reach out to others, and this alumni Discord is where you will get the doubts cleared after your course is done. So once our course is done, you will not stop practicing, right? You'll keep practicing. Maybe not regularly, but you'll keep practicing and you'll still be stuck somewhere or the other. And as a part of your Smart Interviews Smart Coder program, we offer you this service of clearing your doubts whenever you ask us. Even after 1 year, even after 2 years, you post a query, you will definitely get a response from us. And that is what this alumni channel is for as well, basically. So this is like lifelong service. As long as the company is operating and we are able to actively answer your queries, we'll be answering your queries regularly. And it is going great till now, at least. And I know it will go great forever. DSA 29 also lifetime. So any access that you have got during the course, you will retain that access forever. All your accounts, all the reports, leaderboards, rankings, score timeline histories, the Discord groups, etc., whatever access we gave you, you will be retaining that access forever. Of course, the videos will expire. Videos you will not have forever. Videos will expire after 12 weeks. So on every video, it will be written, right? It will be expiring on some March, some date, 2023. You would have seen it on every single video. It will be written some March 29 or something. I don't remember exactly. So whatever that date is there, which is written March 11th, that is the date on which all the videos will be, all the video access will be revoked, irrespective of the number of credits left for you. Yeah. HackerRank questions, Smart Induce primary, Smart Induce basic, everything. You'll retain access to everything. Whatever you gained access to it during the course, you'll retain access to it forever. So yeah, that I think pretty much sums up all the questions. And of course, not to forget to mention that you should also share your experiences in this alumni channel, guys, just like all the other people are sharing your interview experiences, whenever you have referrals open in your company, whenever you have whatever you think you can do to help others, you should also contribute from your side so that it will benefit everyone. And yeah, that's it. We are planning to do more things with the alumni Discord in the future. We are planning to introduce a few more things, events, activities, establishing proper alumni network and letting you reach out to others, letting you know who, like, let's say you're applying to a company, you want to know if any Smart Induce alumni is there in that company who can give you a referral. So letting you know those kind of things, all these different kinds of things are there in the works. So yeah, join and keep checking it regularly. As long as you do not turn off your Discord notifications, if you remember, you are connected to us. The minute you turn off your Discord notifications, you're completely disconnected from us. Will we get a completion certificate after the course? No comments on that. So we are offering completion certificate for all the batches that have started uh, after December, after November or December. But for you guys, I cannot guarantee anything. Most likely, I can try to get something for you. All right. Now let us move on to the next question, everyone. And this is where things get a bit more interesting, shall I say? Yeah. You may also want to drink some water. Yeah, I may have to change some values of the weights of the edges after I explain, or to fit my explanation a bit later. But let's go with these values for now. So given an undirected weighted graph and two nodes, source and destination, you need to calculate or basically weight here represents the distance between nodes. So 4 to 10 has a weight of 5, means the distance from 4 to 10 is 5. Distance from 4 to 14 is 11. Like that. Whatever weight do we have here is basically the distance between the nodes. You need to calculate the shortest path from source to destination. Calculate the shortest path from source to destination. So instead of counting edges, you need to add the weights along the edges. In this example, let us take source as 7 and destination as 5. No, not 5, maybe 12. Yeah, I may have to adjust the values a bit later, but we'll go with this values. Source is 7, destination is 12. So do you know of any algorithm which will help you give shortest path in a weighted graph? That is right. It is nothing but this algorithm. It is nothing but this algorithm. It is nothing but Dijkstra's algorithm. It's not Dijkstra's or anything. It's basically Dijkstra's, where you pronounce J as Y because it is a North European name. Just like Thor's hammer. What is the name of Thor's hammer? Exactly. Thor's hammer is Mjolnir. So where you pronounce J as a Y, basically. Jason, I saw that. Yeah. Yeah, it is Mjolnir. Jonathan. Yeah, one of those things. In an interview, I guess. Anyway, so J should be pronounced as Y. That is Dijkstra's for us. Do not call it as a Dijkstra's or anything crazy. And please educate your friends as well when you're talking about Dijkstra's with your friends. Why will you talk about Dijkstra's with your friends? I don't talk and then correct them somehow. Maybe you can talk about Mjolnir and say that, hey, it's same with Dijkstra's. Anyway, moving back to Dijkstra's algorithm, and let's try to understand what exactly Dijkstra's is. So before we start Dijkstra's, I'll tell you what Dijkstra's is in two simple words. Dijkstra's in two simple words is basically greedy DFS. Dijkstra's algorithm in two simple words is basically a greedy BFS. Ask them to pronounce Dijkstra's or pay 100 rupees, just make money out of your friends. Yeah, definitely. But they can also throw a punch at you by saying that punch means not literally a physical punch. By saying that all proper nouns can be pronounced in however way you want. Proper nouns do not have proper pronunciations and so on and so on. Of course, if they know grammar rules and everything, it matters. But yeah, Dijkstra's is basically a greedy BFS. So yeah, it makes sense for you to be greedy by asking them to pay 100. Let's move on to the discussion here. Why doesn't it move? Yeah, it moves now. So look, guys, funda is very simple. Greedy BFS. So if you think in that direction, it will be dead easy for you. So what I'm going to do is I'm going to start off by creating this extremely important array known as a distance array. Distance array, what we do is basically maintain a distance. (14, 15, 16, just till 16, right? We can just extend it a bit more. 15 and 16. Okay, distance array will maintain the distance. So before you start with your algorithm, you don't know the distance to any node. So you will assume that I cannot reach them. You will assume that the distance to reach all these nodes is infinite. But here we are talking about distance from source. Source here is 7. But you know distance from source to source is basically 0. Exactly, 0. So except for distance from source to source is 0 basically. You don't know the distance to any other node. So we are starting everything with infinite. Infinite in our sense, you can just use an int max for us. Now we will maintain a collection of available nodes. We will maintain a collection of available nodes. In this collection of available nodes, we only have 0, 7. Available nodes, we maintain distance, element. 0 is the distance, 7 is the element. Only one node is there in the available nodes for now. So because only one node is there, we'll select that node. And now we need to update the distance of all their neighbors. 7's neighbors are 16, 1, and 6. So all I have to do is go to 16 and update its distance as 9. Because that is the weight of 7 to 16, right? That edge. 7 to 16 edge weight is 9. So the distance to reach 16 from 7 is 9. Similarly, distance to reach 1 from 7 is 5. And the distance to reach 6 from 7 is 2. Now, because all these nodes, distances have been updated, all these now become available nodes. 5,1, 2,6, 2,6, and 9,16. Right? We are maintaining distance comma element, right, in available nodes. Did you follow me till here? I'll tell you what to do next. Just till here. Okay. Okay. So whenever we update it, we are adding it to available nodes. Whatever we updated, we are adding it to available nodes. The arrow marks are not correct, but you understand. This is this and this is this. And we are writing it as distance comma element. First number is distance, second number is element. 2,6 means 2 is the distance, 6 is the element. 9,16, 9 is distance, 16 is the element. Like that. Now, let's say now I want to pick the next available node. So the next available node that I am going to pick will be the node whichever has the minimum distance here, which will be 2,6. Why minimum distance node? I mean, obviously we want the shortest distance to reach destination. That is there. But there is also one more reason. I will get back to that reason after a few more iterations. But every time from the available nodes, the node that we are picking is always the node which is having the minimum distance. Out of all the available nodes, the minimum distance is for 2,6 here. So that is what we are picking next. Okay, let's pick 6 as the node and update the distance to its neighbors. So 6's neighbors are 1, 15, and 7. Now first we'll update distance to 15, which is 3. This distance array is basically going to store the distance from source to that node. But source to 15 is not 3, right? 6 to 15 is 3. So how do you know what is the distance from source to 15? Now I want to update this. Exactly. You just add 5 plus 3, sorry, 2 plus 3, which is 5. That is right. So if you know the distance from source to 6, then you can add with the distance from 6 to 15. So distance from source to 6 is 2, 6 to 15 is 3. So distance from source to 15 is 5. So we update 5 here and add it to the available nodes collection, which is 5, 15. Now update 1. So distance from 6 to 9 is, 6 to 1 is 9. 6 to 1 is 9. And what we do is basically distance of 6 plus 6 to 1, right? Which is basically 2 plus 9, which is 11. But if you see, distance of 1 is already smaller than that. So when the distance array already contains something smaller, then we shouldn't update, right? Because we want the shortest distance from source to that node. So we will not update it here. So the distance from 6 to 1 is greater than the known distance for 1 already. We will not update it. And because we are not updating it, it will not be added to the available nodes collection. Now for the last node, which is distance to 7. And now you might be wondering, why 7? We started from 7. We came to 6 from 7. Why are we going back to 7 again? See, guys, whenever we did traversal on a graph, we were maintaining a visited array, right? To keep track of these things. I am showing you that here you don't need a visited array. Because when you try to go back to the same node, now the distance will become double, right? So 7 to 6, you traveled a distance of 2. And when you try to go back, it was 2 plus 2, which is 4. Which is obviously going to be larger than the known distance to reach 7. So it is completely fine without a visited array for us. Because going back to the same node will just double the distance between them, which will anyway not update in the distance array. Yeah, exactly. 0 is smaller than 4 here in this case. And it will anyway not be added to available nodes, and you will anyway not consider it in the future. So that is why we don't need a visited array here. 7, you try to update, but 7 contains 0 already. But if you do distance to 6 plus 6 to 7, it will become 2 plus 2, which is 4. Obviously, 4 is bigger than 0. We don't update. Can you note down till here? Then I'll show you how this will get complicated because of 2-3 things. Note down what we are doing till here. Then I'll show you 1 or 2 small complications that arise. Note down the purpose of distance array. Note down what we are storing in available nodes. Note down how we are choosing which node to pick next from available nodes. And note down how the distance array gets updated once you pick anything. And also note down when will you add anything to available nodes. And if you want me to repeat any part of it, please ask me. Repeating everything might take long, but 1 or 2 things I can repeat. Why are we comparing the updated distance 2v with 1v5? Updated distance of 2v with 1v. I don't understand your question. Two plus 9 with 5. 2 plus 9 is the distance that you got to reach 1. So you could reach 1 from 7 and via 6, right? So when you came to 1 from 7, we already updated distance as 5. But when you're coming via 6, now you're getting distance as 11. So that is what we are comparing. The known distance, which is 5, and the existing and the current computation distance, which is 11. And because 5 is smaller, we did not update it. Okay. Namika, we are not using a visited array because when you try to go back to the same node, the distance will be just double of what you calculated already. So 7 to 6 is 2. Again, if you try to go back to from 6 to 7, it will become just 2 plus 2 again, which is 4. Similarly, it happens with any node. Like for example, you are going, let's say, here, and then you're coming here, let's say. That is still going to be smaller than uh, distance of 7, which is 0. Or we can take any other example. So let's say you are trying to calculate for 1, maybe. The known distance to reach 1 is 5. So if you try to calculate here to here, it will be again 11 plus 11, which will be greater than the distance to reach 5 already. Because the distance will be greater, we will not update it. Fast, guys, last 30 seconds. When do we add element in available nodes? We add element to available nodes only when its distance has been updated in the distance array. How do you choose the next node from the available nodes? We choose whichever node has the minimum distance out of all the available nodes. All right, let's continue. For some reason, many of you have your videos off. I don't know why. Session is not done, and it is a slightly complicated question as well and solution. And it's not complicated till now, but it will get complicated after this. All right, now let's do a dry run for a few more iterations and see what complications arise here. Now 916, 51, and 515 are there. We'll pick the next available node, which is minimum of available nodes, which is 51 or 515. 515 anyway doesn't update anything, so we'll ignore it and we'll just go to 51. Each element in distance will contain the shortest path of that node from source. That is correct. So distance of anything is basically shortest path from source to that node. Now, let's say I pick 5,1 now. Now I need to update all the neighbors of 5. Again, sorry, now all the neighbors of 1. 5 is distance, 1 is an element. Now we need to update all the neighbors of 1. So 1 is here in the middle. All the neighbors of 1 are 7, 6, 9, 5, 4, 14. All these are neighbors of 1. So let's start updating them and see what will happen, okay? First, I'll try to update the distance to 14. So distance to 1 is 5 plus 1 to 14 is 3. So 14 will contain 8. Then 4, 5 plus 8, which is 13. Then 5 plus 11. 5 plus 11 is 16. Then we'll update this 5 plus 7, which is 12. Then we'll update to 6. 5 plus 9 is 14. 6 already has 2, so it will not update. Then we'll update this. 5 plus 5 is basically 10, so we'll not update that. So what all got updated, we need to add to available nodes. 13, 4, 16, 5, 12, 9, and 8, 14. These all will go to available nodes. And now we are done with 1. Okay. So now, when you picked 1 from here, Yeah, we can use this example. When you picked one from here, you had all these nodes in the available nodes collection, right? When you are picking one. So now, if you already updated all the neighbors of one with a known distance to reach one as 5. Now, what I'm asking you is, once one is removed from available nodes collection, is it possible that one will enter available nodes again? Is it possible that one will enter available nodes again? If one should enter available nodes again, then one of the other available nodes should update the distance of one with something smaller than 5, right? Are you following? If one has to enter available nodes, its distance should become smaller. Only then it will enter available nodes. Yes, exactly. So if you see all the other nodes, everything else has a distance greater than or equal to 5, right? Means it is not possible to get a distance of distance to reach one smaller than 5. If you try to come from 16, it will be 9 plus some distance. If you try to come from 4, it will be 13 plus some distance, 16 plus some distance. Are you following? None of these nodes can update the distance to 1 anymore. And by implication, we are basically saying that when you remove anything from available nodes collection, then at that point it has the best or smallest possible distance from source. When we remove any node, we are saying that at that point it has the smallest possible distance from source. We are basically saying that it will never update again. Looking at your expressions, I strongly feel that it did not go well. So let me try something else once. Okay, 1,5 is 1 basically. 5,15 also we can remove. It doesn't have any neighbors, it's just 6, so it doesn't update anything. All right. So to understand it better now, try to answer my next question. Out of the remaining available nodes, now we need to pick one node using which we will update the distance to the neighbors, right? So which node should we pick such that we get the best distance? 8,14, because logically it has a minimum distance out of all. So that's why we are picking 8,14. So now my question to you is this. Let's say you did not pick 8,14. Now the distance to 14 can only be updated by one of these other nodes, right? 4, 5, 9, and 16. distance to 14 can only be updated by one of these nodes, 4, 5, 9, and 16. Can any of these nodes reduce the distance to 14 any further? No, exactly. No, it is not possible. Because their own distances are itself greater than 8. They cannot reduce the distance to 14 any further. Distance to 14 is already 8. Thereby, we are saying that it is the smallest possible distance to reach 14 from source. Got the point now? It's not about one updation. It is about whatever is at the time of removal from the available nodes collection. That is the final update that you get. Because you're removing it because it has a minimum distance. And also you're removing because no other node can update its distance to anything smaller than that. Only update if the distance is less than the previous. Yes, that is correct. Got the idea now, guys, how we are saying this? Finalizing the smallest possible, as no other can be smaller. That is correct. For 14, because you're removing it from available nodes, it means that it is the smallest. It is the smallest means no other node can update distance to 14 anymore. If no other node in the available nodes can update distance to 14, means you found the best distance to reach 14 from source. That is right. This is the other reason of choosing the small distance every time, the minimum distance every time. Because we found the best distance to it. It cannot update any further. Now we'll use it to update all the neighbors. All right. Now, can there be negative weights? No. If you have negative weights, Dijkstra's algorithm will not work. There is a different algorithm for that. It is called Bellman-Ford. So Dijkstra's algorithm will work only when there are positive weights. So now here, guys, if in the available nodes, now I'm going to show you that it is possible that we can have a duplicate in the collection. It is possible to have multiple nodes with different weights. Sorry, multiple entries with different weights and same node. How is it possible? So let's say in this graph, now the next minimum that we pick is 9,16 and it doesn't do much. Or maybe it does. Yeah, it does. It does. So 9,16 is the next one that we pick. Sorry, 9,16, right? It's a 16. Okay. It will just add 2 to the available nodes collection. That is 16 plus, 9 plus 13, which is 22. So go to update distance as 22. Add 22, 2 to available nodes. And the next, oh yeah, we completely missed 8, 14. Undo. It's not 9,16 that we pick next. It is 8, 14 that we pick next. 8 is smaller than 9, obviously. And let's update the neighbors. One will not update only 4 will update. 4 will update to 8 plus 11, which is 19. But 4 we already know 13, so 4 will also not update. So 8 comma 14, nothing will update. Then 9 comma 16 we update 2 to 22 and add 22 comma 2. And then we get 12 comma 9. So this is where things get a bit interesting, guys. For 12 comma 9, the node is 9, distance is 12. Update neighbors of 9. Neighbors of 9 are 1 and 13, right? Distance to 1 will not update for sure. Only distance. Distance to 13 will update to 12 plus 13, which is 25. 25 is smaller than infinity, so we'll add 25 with 13. And the next node that we pick will be, so 12 comma 9 is done. Then you pick 13 comma 4. 13 comma 4, let's say you update something, it doesn't matter. And eventually you will pick 16 comma 5. 13 comma 4, you'll update the neighbors. I'm not concerned about that. Now we'll update 16 comma 5 now. So when you remove 16 comma 5 from the available nodes collection, what will happen? The neighbors of 5 are 1, 13 and 12. Now when you try to update the distance to 13, what will happen? It will become 16 plus 2, right? Distance will be 18. So you're adding 18 comma 13 to available nodes. Along with that, you'll also update 12 and add whatever distance it will take. But what we have to focus on here is this, which is it is possible that we can have duplicated entries entering our available nodes collection. From 9, you updated the distance to 13 as 25 first. So you added 25 comma 13 in available nodes. But when you're coming from 5, now you updated its distance as 18. So you also added 18 comma 13 to available nodes. In this way, it is possible that there may be multiple entries for the same node with different distances. What should we do with these duplicated entries? What should we do with these duplicated entries? Process them exactly. How do you handle it? Only keep the ones with the least weight. That makes sense? That is right. Only minimum weight node is required here. That is right. So if you want to maintain only the minimum weight node, you should know first 13 exists. If it exists, you should know what is its distance. And then remove it from there. This data structure, this collection that you're using for available nodes, which data structure will fit our need? Every time we should pick the minimum. Every time we need to pick the minimum. Thank you. It will be a min heap. It will be a min heap. Okay, let's say you're also using hash map instead of min heap. Not exactly hash map. You will need a tree map, an ordered map, right? To get minimum in logarithmic time. If you're using hash map, you will not get minimum in logarithmic time. It will take linear time to get minimum. Tree map will give you minimum in logarithmic time. Hash map or tree map, whatever it is. Sorry, tree map or min heap, whatever it is. The ordering of the elements has to be maintained based on distance or element. Order of the elements has to be maintained based on distance or element. Distance, right? Because we need minimum distance every time. Now, if the ordering is based on distance, and if you want to search for duplicate and remove, your tree map will not help you, right? Because your tree map is ordered based on distance. If you want to find the value of 13, it will take linear time again. Because it should take every single node in the tree map. Are you able to understand the point I'm trying to make? So it is not possible to remove the duplicate entry, old duplicate entry efficiently. You can do it by looping on all the nodes. But that is not efficient for us. No matter whether you use min heap or tree map. Min heap is obvious. You don't get any information other than the minimum. So that is completely useless there. And tree map is ordered based on distance, not based on element. So that is useless there. Okay, that is the point. And that is why we need to handle duplicates in a simpler way, which is whenever you remove a duplicate, first you will remove 18 and only after that you'll remove distance 25, right? When you're removing nodes, min distance will be removed first and only after that others will come. So whenever you remove anything, you simply go and check, is it the best to the distance that we have there? 18, 13 will match with the distance in the array. But when you remove 25, 13, it will not match with the distance in the array. Then you will know that it is a duplicate. Then you will know that, okay, you don't have to do anything with it. You can just ignore it and move on to the next one. And at the end, once this entire processing is done, where will you find the answer? Is having duplicates inefficient? Having duplicates is not inefficient. Finding the old duplicate and trying to remove it is inefficient. Perfect. Distance of destination. Perfect, guys. Perfect. You got it. Distance of D will be the answer at the end of all this process that we are doing. Shall we try writing the code for this? Sorry, I'm not going to use any specific syntax. I'll use the regular syntax that I'm writing. No, I'm not going to show you code live coding. I'm going to show you code on the pseudocode syntax that I'm using all these days. Pen paper coding. Except it's not paper, it's OneNote, which is technically a notebook containing pages. It's a paper. Anyway, let's write code for it. I'll explain you the time complexity, but after I write the code and then I'll explain you what is the time complexity here. Yeah, writing on pen paper is the most required thing for us here. Okay, guys, now let's simplify it. Let's dumb it down. Okay, so that we understand how to convert it to code step by step. So now I told you that it is greedy BFS, right? You know that min heap is also known as priority queue. You know that min heap is also known as priority queue, right? So instead of tree map, we'll just go with priority queue. Now this is just a BFS that you're doing. Instead of queue, you're using priority queue. You'll remove everything one by one from priority queue and you'll update the distance to neighbors. Whichever neighbor's distance updated, you will add it to priority queue again. Do you see the pattern? This is exactly what we did in BFS, right? Instead of priority queue in BFS, it was a queue. That's it. So we maintain priority queue. We remove one by one from it. we update the neighbor's distance, and whichever distance updated, you put it back in the priority queue. If you dump it down, that is the entire logic. Okay, so let's see how this will convert to code. And please try to write along with me, or before I write, or without seeing on my screen. Basically, I want you to use your brain more than, writing after looking at what I'm writing or blindly copying. You're given a graph, source, destination. Just a reminder, it is a weighted graph. This is the first weighted graph problem that we are dealing with. So it will not contain integers. It will contain pairs of integers. Element, comma, weight, element, comma, weight, element, comma, weight. So the type of the graph will be something like vector of pair instead of integer. If it is C++, or Java, array list of pair, Python list of pair. In C++, when you use the inbuilt pair, they call this first and second. Dot first and dot second. In our graph, when you are building the graph, first is the node and second is the weight. So keep this in mind when we are writing the code. Now let's say I'm writing the code here. List of tuple, not list. List of tuple is recommended in Python. Or you can also go with list of pair, which is a pair class, but not required. Okay, now let's write the code. What is the first thing that we need here? Distance array, right? Distance array is the first thing that we need. So let's create a distance array of size. We'll first store the size of graph here. V equal to graph dot size. Then create a distance array of size V. Initialize with int max, which is equivalent to infinity in our scenario. And initialize distance of source as 0. This is the initial step that we have on distance array. If you remember, all infinity except source, distance will be 0. Then we need the priority queue. Here, priority queue should be of type pair again, right? Because we are storing two things in our priority queue, element, comma, node. Or you can also use a tree map, which is also fine. Sorry, distance, comma, element. That is right. So pair of int, comma, int. We'll just call it a heap. Because our priority queue is basically a pair type, which is not a primitive type, you may also have to write a comparator for this to tell how to compare in the priority queue. Or you can also use a tree map and simplify things. But I'll show you how to use it with a heap. moving ahead to the next part, we know that the first thing that we are going to add to the heap is basically, tell me, what is the first thing that we add to the heap? Exactly, 0, s. Perfect. You got it, guys. 0, s. That's right, 0, s. And we will write a logic while not empty. We will extract whatever pair type that we have. We'll call it current node from heap, get min or delete min. To simplify things for us, I'll call this U, which is current dot second, and distance D, which is current dot first. In heap, first is distance, second is element, right? So that's what I'm writing here. Now here we need to write two conditions, which I'll tell you what they are after we finish the rest of the code. Just leave 2 lines of space here. No, first is element. Sorry, first is distance, second is element. See, we are pushing 0, s, right? And the reason why we are pushing it like that is because of simplifying our comparisons in the comparator. And if you're using C++ especially, you also don't have to write a comparator for this. If you're maintaining a pair of int, int. C++ inbuilt pair type is natively supported, and you don't have to write a comparator. Of course, you can customize all these things on your own. I mean, doesn't matter, like, this is first, this is second. If something is convenient for you or inconvenient for you, you can just change it. As long as you understand what is exactly that I'm writing, that's it. All right, guys. Now, what did we do? What did we say we will do? We will remove from heap, loop on neighbors, update neighbors, whichever neighbor updated, add to the queue. Remove from heap is done, right? Now loop on neighbors. After we loop on neighbors, whichever neighbor is updated, we add it to the queue. For pair of int, in for the neighbor x in graph of u. Remember, guys, till today we were writing this for each loop with for int x in graph of u. But now instead of int x, now it became pair x because it is a weighted graph. Because it is a weighted graph, it became a pair x. And then we'll just loop on the neighbors. First, I'll extract the node and weight from it. Node is equal to x dot first. And weight is equal to x dot second. Can you tell me what is the condition that I have to write here before I decide if I should update or not in the distance array? No, Tarun. This is graph, right? In graph, if you remember, first is node, second is weight. check visited or not. We don't have visited array here. What do we check, guys? What do we check? Incorrect, Mahesh. Incorrect comparison. Incorrect comparison. Perfect, Monica. That is right. Yeah, that is perfect. See, guys, now let's say you are at some node A. We have source node. And we have B, C, D as neighbors of A. So you should know the distance to reach A from source and the weight to reach B. That you should compare with the known distance to B already. So this A instead is our V, nothing but our V. Sorry, nothing but our U. And this is a V here. So distance from source to U plus the weight on the edge U to V. If it is smaller than the known distance to V already, means you don't know if there is, another path to V. You're comparing with that. You're basically checking, should I go like this or is there a better path? That we already know. If it is less, then we update it. Distance of V is equal to distance of U plus W. And what else should we do here? What else should we do here? Exactly. Perfect. Add to the heap or the priority queue here. Exactly. Heap.add. Heap.add. The node that you updated is V. And the distance that you updated it with is distance of V. And at the end, what do you write? Return. Distance of D. Perfect. Return distance of D. Simple logic, right? See, this code is very similar in structure to BFS that we wrote. You loop, remove one by one from the queue. Sorry, basically you start with the queue, remove one by one from the queue, remove loop on neighbors, add to queue, remove loop on neighbors, add to queue. That's what we did in BFS. Same thing we are doing here, except we check the distance and then add to the queue. That is the only difference. Now these two lines, I asked you to leave two lines here, right? Now I'll tell you what those two lines are for. The first thing that you should do here is check if it is a duplicate. Yes. How do you check if it is a duplicate? Or if it is a inefficient duplicate or duplicate with a longer path, longer distance. Tell me, guys, if exactly distance of U will not, okay, you're checking. Distance of U will have a smaller distance, not greater distance. Not equal to D or less than D. Anything is fine. If distance of u is not the same as the distance that you have in the heap, then you can ignore it. Just continue. Useless. It is a duplicate node that we are getting now. You remember, right? Distance array will contain the smallest distance always. So whatever distance you remove from the heap, if it is not the smallest distance that you know to that node, then it is duplicate already. And what is the second condition that we should check here, guys, to optimize things? We can check if perfect, Samad, that is right. U equal to destination. Then, yeah, you can break or you can directly return. Return what? Distance of u, which is nothing but d. I see that's wrong. You can't say you will not return anything because my return type is incorrect. You should correct my return type instead. Return type is integer, not void. Yeah, return d. D is also equal to distance of u because you already checked here if they are not same. And the only case where it will come to the next line is when they are same. So obviously you can check, you can directly return d or distance of u. I will give you time to make a note of it. But before that, just hear out the plan for tomorrow. So let's say that I have roughly at least 1.5 hours of content to discuss. 1.5 to 2 hours of content is left for us in graphs. Depends on how you perceive and how fast you respond and the various factors. But at least in worst case also, 1.5 hour content is left over for us. And tomorrow's plan is basically, we'll continue with graphs. We'll solve few more problems. We'll solve, different types of graphs, some advanced problems and everything. And after that, before we start with the final lab session, we will discuss few things which are related to next steps. What should you do after your course is done? How to hunt for jobs, resumes, how to create resumes, where to apply, how to reach out to people, etc., etc., etc. And if possible, we will also try to arrange an alumni talk that I promised you somewhere in the middle of the course. But I am trying very hard for few alumni to talk tomorrow, at least one. So that will also be there. Then that alumni will be a working professional who will tell what his or her experience was in this job hunt that they had. How did they apply? What did they do after the course, etc., etc., etc. And you can probably ask few questions to them. Again, I'm trying my best to get them, but I'm not promising anything. I am trying my best to get an alumni to interact and discuss with you and share their experience about that. Obviously, there'll be an experienced person, so you can ask all sorts of doubts. And the next thing and the last thing is tomorrow we'll have lab session. Lab session will be our last lab session. And in tomorrow's lab session, we'll be implementing all the problems that we discussed today and tomorrow. Obviously, in the lab session, you'll not solve easy problems. You'll only solve tricky problems. So tomorrow, you'll either solve Dijkstra's or some 1 or 2 complicated problems that we are going to discuss tomorrow. That will be the target for the lab session tomorrow. And that will be your final lab session and final ending. And please don't get lazy. And do not skip tomorrow's session under any circumstances, no matter what you have. I am trying to do a lot of things for tomorrow. So yeah, definitely attend tomorrow. And any doubts, you can stay back and discuss with the mentors. I'll leave the screen on for you to note down here. Same timing, full 4 hours. We will have full 4 hours because 2 hours of content itself is left. Then that alumni talk, resume review, all that will take at least 1 hour. Then at least bare minimum 1 hour of lab is required to solve at least one bare minimum of one problem. So final contest we'll discuss tomorrow. Is the alumni talk after the lab? No, it will not be after the lab. That will be pointless, right? Depends. And if we see that the lab time is going to be insufficient, we may have to forego the lab and we may have to conduct it at a later point of time. Whatever it is, I'll tell you tomorrow. But our priority is concluding everything properly. Lab is a second priority for us, obviously. Alumni talk, if it happens, then definitely lab will take a hit. Cool. Just one last thing, guys. Just one last thing, just a second. Yeah. Second mark activity. I forgot completely. Room setup tour. We'll do it tomorrow. Definitely, why not? Yeah, I have enabled second mark activity just now, guys. Please don't forget to mark your activity.
Recording stopped.
And if you have any doubts, please stay back and discuss in the breakout rooms. And if you did not note down properly whatever you have on the screen, please note down before you exit. And do not forget to mark your activity. Repeating again, do not forget to mark your second mark activity. Please join the breakout rooms and discuss with the mentors. I'll leave the screen on for the next 10 minutes so that you can note down everything properly. And see you tomorrow, guys. Don't waste the last breakout rooms, guys. This is your one of the last breakout rooms. So definitely utilize it very well. Ask your doubts, clarify everything. Yeah. Thank you, guys. See you tomorrow.